So on to 7.5, and I've started entering the data. I just need to finish it off here. So is everybody good up to this point? You have the data entered? Okay. So this is average growth rate for some cherry trees. And we want to construct a scatter plot. So if I do this much, I can come to the second y equals, turn my plot on. And I want a scatter plot, list 1, list 2. That's good. So if I graph it, let's do a zoom data here, or zoom stat. I think I have something funny entered. Because it looks like there's a general trend, but then there's this one that's way off, which as I look at my table, that I don't think that should be the case. So I need to go back and double check. Oh, look at that. I had a 6.5 instead of 9.5. So looking at the scatter plot, really not a bad idea, just to see if you have made a mistake or have an outlier or something like that. So there we go. You have a scatter plot that kind of looks like that. So it has this kind of curve that looks logarithmic, kind of as it goes towards the right there. And so we're asked to do a log regression in question number 11. And so when we do a log regression on the calculator, it's going to be a log base e. So it's going to be the ln of x. So here, if I come back to stats and calculate, I'm going to scroll a little bit further. Just to be careful, so you'll see number 9 is the ln regression. That's what I want to use. I came down as far as the B, which is a logistic regression. Be careful, because it looks, if you just look at the first 3 letters, it looks like it's log, but it's not logarithm. It's something different. So I want to use this ln regression, so the natural logarithm regression. And I want to store this in y1. So there are the values I get. I want how many decimal places? 100th, so 2 decimal places. 5.93 and 6.28. So that's what my logarithmic regression equation looks like. And again, just remember the natural logarithm is a log base e, where e is Euler's constant. Good enough for number 11? Okay. So in number 12, we want to describe some characteristics of the function. So let's look at that graph again. There's my curve. To find the x-intercept, I guess I might need to change my window so I can see a negative y value here. And we can calculate that 0. Here I can see my y is negative, so I know I'm below the x-axis. That'll be my left bound. Now my y is positive, and I can guess there, and I get 0.38896. Everybody getting that? So x-intercept is about 0.389. And there's no y-intercept. Because again, it's logarithmic, hasn't been, if with a logarithmic function, if it's shifted to the left, it could have a y-intercept. But when we do these regressions, because of the form it's being written in, it won't have a y-intercept. Domain and range for this question. Well, here I want to look back at the information we were given in the question. So it's the average growth rate for 12 of these cherry trees. The trees were 1 year old and were all 6 feet high to begin with. That's all we know. So for our domain and range, what does x represent in this question? So x would be this first column in the table, right? So that was list 1. So the age of the tree. So are there any restrictions on what the age of this tree could be? Well, it can't be negative. And because this data is just from when it's 6 feet tall, so after 1 year, we'd have to look at kind of when it's, possibly when it's over a year, or we may want to look here and see, well, the x-intercept, we can't have a negative height for a tree. So we could say, well, maybe it's good starting at this x value. I can't remember what I put here. What did I put? Oh, I did use that. Yeah. So x has to be greater than or equal to this 0.389 because the negative tree height doesn't make sense, and the negative height would be the y value. And the y values are the heights of the trees. So again, those can't be negative, but we'll say they can be greater than or equal to 0. Or we could argue that, well, seed is planted underground. Is that a negative height? We just won't get into that. And this function, as you go from left to right, increasing or decreasing? Increasing because trees grow up. There we go. And if a tree is 20 years old, how tall do we expect it to be given this model? So we know the age, which means we know an x value. So we can plug in that x value into our regression equation, or we can look at it on the graph. I just need to make sure my x max goes that far. So let's go up to 25. And when I trace, I'll just type in the 20. Oh, it's not doing it. So maybe I will, instead of trace, I will calculate a value when x is 20. And I get 24.75. We're all good with that? Did this question ask for so many decimal places? Nearest foot. What? That's not the nearest foot. Oh, nearest tenth of a foot. I just can't read. There's my problem. I think I need a spring break. And then to the nearest tenth of a year, average age of a tree that's 11 feet tall. So again, we want to look at our graph. We know the height. So I want to make sure my y max, it does go above 11. That's good. So I'll enter 11 as a height. Graph them. And find the intersection point. Close enough. So here's 10th of a year. I'm getting 2.2. Everybody's 2.2. Oh, look at how easy this stuff is now. You've done regression so much. Good. And it's all similar. It's just a matter of choosing the right regression when we do that regression. There we go. That's the end of the chapter. We'll do some review the week we get back. And the test will be, that Wednesday. So the second day we're back. Good-o. All right. Have a fantastic field trip and spring break.